So we're going to go over section 5.4 of our textbook, the Fundamental Theorem of Algebra, and we might shorthand that FTOA. So if I write FTOA, I'm talking about the Fundamental Theorem of Algebra, and fundamental theorems are kind of like the linchpin for for everything related to algebra. So this is actually a big deal today. And there are a few other fundamental theorems. You have the Fundamental Theorem of Arithmetic, and you also have the Fundamental Theorem of Calculus, which are very common, very useful as well. We make use of those a lot. So what does the Fundamental Theorem of Algebra say? So the FTOA, and this may not seem like a big deal at first, okay? The Fundamental Theorem of Algebra says every polynomial, we'll call it P of x for a general polynomial, has a zero. Okay, so there is, for any polynomial, there is something that makes it equal zero. Alright, so, and that's what we mean here. P of x equals zero always has a solution. Now, a few things here. They may not be real, so they may be complex. Alright, so it may not have a real zero, but it could have complex number zeros. We will have zeros. Okay, now what that leads to then, remember once we find a zero, we can do synthetic division to divide and we get a new polynomial. Okay, so, well, let me say that again. When you find a zero, you can, let's call it k, then you can divide your polynomial by x minus k, or in other words, factor out x minus k, and then you have a quotient polynomial. Well, the quotient polynomial is a polynomial as well, so it has a zero. Alright, so that means that you can divide by its zero and get a new quotient polynomial, and basically what you're doing is you're factoring. Okay, and so this leads to something very, very important that often is referred to as the Fundamental Theorem of Algebra, but we could also call this the linear factors theorem. And it comes directly from the Fundamental Theorem of Algebra through the process I just explained. And that's let's let p of x be some sort of nth degree polynomial. So if a to the n, x to the n, plus blah, 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 out to a to the 0. Okay? Then p of x can be factored as some sort of leading coefficient times a bunch of linear factors. X minus k sub 1, x minus k sub 2, out to x minus k sub n. Alright, and there are a few key points that I want to point out here. First of all, we're saying then that we're saying all polynomials can be factored as n linear factors. Okay, and here n, by n we mean the degree. So that means all fourth order polynomials can be factored as 4 linear polynomials multiplied together. Okay, so in other words, just like if you take the number, let's think of one, 42. Okay, so here's the comparison. You take the number 42 and I can factor it down. So I can factor that down as 6 times 7, right? And then I can break down 6 as 2 times 3, and the 7 is prime, so it doesn't factor. And so I could rewrite 42 as a product of prime numbers. And I can write every single number as a product of prime numbers, and that product of prime numbers is kind of like this unique serial code for every single integer. And this is actually the Fundamental Theorem of Arithmetic that says that. Okay, so now for polynomials, we're saying there's a similar idea, except instead of prime numbers, we're talking about linear polynomials. So every polynomial can be broken down into a product of n linear polynomials being multiplied together. So these linear polynomials are kind of like the prime numbers for polynomial world, if you will, okay? Now there's a few things we need to point out here. First, the historical note. Okay, so here's some history. This was proven by a guy named Frederick Carl Friedrich Gauss. All right, and Gauss was in the late 1700s, early 1800s, and Gauss is considered to be one of the top 3 mathematicians of all time. Okay, so he's in the top 3 club. Of all time, so you might call him the GOAT or one of them. All right, so Gauss proved this as his dissertation. So to get his PhD, all right, at the age of 22. So for a long time, mathematicians thought that every polynomial had a zero, but we couldn't actually prove that. Well, Gauss, at the age of 22, okay, so about the age of some of you, actually did prove this fact and earned his PhD in doing so. Okay, so Gauss was a pretty sharp guy. All right, so that's one note. The next note we want to point out here is that even though you have these k zeros, you have these, these n zeros, you have n things that make the polynomial zero, some of them might actually be the same thing. All right, so you might have repetitions. So you may have some zeros repeated. And we use this word already, but you call this the multiplicities. The multiplicities is the number of times that zero shows up in your list. The other thing is that some may be complex numbers. Okay, so they're not always going to show up just a bunch of, you're not going to always have n real terms. Okay, so let me give you a couple of quick examples of that. So for example, here I might have the polynomial p of x equals x squared plus 2x plus 1. Okay, now that factors, well, let's change that a little bit. Okay, my eraser's not working. Let's change this to x cubed, 2x squared times x, okay? And now I can take out an x and have x squared plus 2x plus 1. And then that's going to factor as x plus 1 times x plus 1. So see, it was a third degree polynomial, so I knew I was going to have 3 linear terms when I completely factor it. But notice that some of them are the same. So we would more commonly write this as x times x plus 1 squared. And that's where the multiplicity comes in. That's multiplicity 2. But that all it's saying is that this negative 1 is a 0 twice for this polynomial. Okay? Now to illustrate the second point, let's think about maybe q of x being x squared plus 1. Okay, so I'm trying to think of a 0 that when I square it and add 1, I get 0. That may be difficult to think about until we get into complex numbers. So this actually factors as x plus I times x minus I. And see, it was a degree 2 polynomial, so I would expect 2 zeros from the Fundamental Theorem of Algebra, but they're not real zeros, right? They're x plus I and x minus I are zeros here, are complex numbers, which is totally fine. Okay, I hope this is making sense to us. All right, now this this idea relates now to the graph as well. So here's a couple things that get pointed out from this. Okay, so let's say on graphing. And graphing only has one R. So one, let's let p of x be a x to the n plus blah blah blah. We don't really care out to, so that's a sub n out to a sub 0. All we really need here is the degree. Okay. Then the graph of p of x has at most, okay, one is we can say n x-intercepts, right? So a degree 3 polynomial can only have, at most, 3 x-intercepts. If you try to graph a third-degree polynomial and you keep crossing the x-axis 4 or 5 times, you've done something wrong, right? You can only have n x-intercepts. And at most, n minus 1 turning points. Okay, now what is a turning point? So in a turning point, I mean something like this. If your graph looks like this, okay, your turning points are right here. So this is a turning point, turning point, turning point. That's where it changes direction from up to down. Okay, so these are the turning points. Okay, so I can look at a graph then and get some sort of idea of its degree simply by the number of times it crosses the x-axis and the number of turning points, okay, because that relates directly to n. All right, the other thing is multiplicities, and we talked about this earlier. To be honest, I got a little ahead of myself when we were talking about graphing factored polynomials. We talked about two things. We talked about the end behavior, and we talked about the multiplicities of the intercepts. And so I'm going to explain again what happens there. So with multiplicities, if let's say 0, what am I trying to say? K is a 0 with multiplicity m. Okay, so that means my polynomial factors like this: a x minus k to the m power times some other stuff. We don't know what else is there, okay? The m tells me some things about the graph. Okay, so if m is odd, the graph passes through the x-axis at k. Okay, so it'll look something like this. Here's your graph. Here's the value k. If k is an odd multiplicity, it's going to do something like this. It's going to pass through at k. All right, well, what else could it do? If m is even, the graph does not pass through, and we talked about this once already. We're just kind of reviewing this again. The graph does not pass through. It hits the axis and bounces off. So it bounces off the x-axis at k. Another way of saying bounces here, and this is a mathematical term, is kisses. Okay, and that makes some of us giggle, I know, but it can kiss the axis by hitting it, kiss the axis, hitting it, and bouncing back. All right, so something like this. If you had an even multiplicity, then your graph is going to, is going to hit k and then bounce back, something like that. Okay, so that's where the multiplicities come into play. So now we know that just based off the degree, we know at most, how many intercepts we're going to have. We know at most how many turning points we can have. And we know if it's factored, we know exactly how the multiplicities affect the graph. Okay, so based off this, I think we can figure out how to graph. For example, we're going to graph a polynomial, and this is example 1 in the text. It says sketch a graph of the polynomial. So let's say sketch p of x, which is x plus 2 times x plus 1 squared times x minus 3 cubed. All right, we're trying to graph this polynomial. All right, so when it's factored for us, so when graphing a polynomial, the first thing we should try to do is try factoring. Try factoring it. Why? Because the factored version of the polynomial tells exactly where my zeros are, which directly relates to the x-intercepts, and my graph, right? So the factoring kind of helps me understand the true nature of what this polynomial is doing. Just like factoring 42 down to 2 times 3 times 7 gives me a clearer picture of what 42 really looks like. Factoring does the same thing for polynomials. Now here, this one is factored for us, so we're good with that. Okay, we don't have to worry about that part. The second part and the third part, which can be done depending, can be done in either order. We can say let's determine the end behavior, and the other thing is find x-intercepts, which should be easy if it's factored with the multiplicities. Okay, so let's take a look at what we have here. Let's see if we can do those last two things. And so what I'm actually going to do here is I'm going to do step 3 first, because I have a factored polynomial. I have p of x equals x plus 2, x plus 1 squared, and x minus 3 cubed. Okay, so my zeros then, let's do it this way. Let's say k for zeros, m for multiplicities. My x-intercepts are going to be -2, -1, and +3. Do you see where I got that? I just got that from here, here, and here. The multiplicities associated with each one of those, let's see, well, -2 is a 0, but in my factoring it only shows up one time, so it has a multiplicity of 1. -1 is a 0, but it has a multiplicity of 2 because it shows up twice in the factoring here. And then 3 is a 0, but it's also it's a 0 with multiplicity 3 because in the factoring here, the 3 shows up 3 times because it's x minus 3 quantity cubed. Okay, so I hope that makes sense so far. What this tells me then is I know something about my graph already. If I come out here, I can try to graph this thing. I know that at -2, I have a 0. At -1, I have a 0. And at 3, I have a 0. So I know that so far. Okay, now the other thing I need to know here is my end behavior. So I'll call it 2, end behavior. And we talked about the end behavior earlier. What the end behavior means is what's going on to the right and to the left as x goes out to infinity, x goes out to -infinity. Is this thing going up or down? And it was only determined by two things. First, the leading coefficient, and secondly, the degree, okay? So if I look at this polynomial, if I took p of x, and instead of looking at it as a factored version of this, I just multiplied everything across. Then the first term, so I'm having to do FOIL method over and over and over, right? I have to square the x plus 1, I have to cube x minus 3, multiply all that by x plus 2. It would take a lot of work to do that, but we don't need everything. All I need is the leading coefficient and the degree. So when I first do this, I'm going to multiply these first three terms together. I'm going to end up with an x. So I'll have an x times the x plus 1. Once I square that, the first term is going to be an x squared times the x minus 3 quantity cubed. When I cube that out, the very first term is going to be x times x times x, which is x cubed. So when I factor out this polynomial, or not factor it, when I multiply it out, when I reverse factor it really, p of x, the first term is going to be x times x squared times x cubed. Remember, we add the exponents, so that's going to be x to the 6th power plus some stuff. Okay, and really the other stuff doesn't matter here. All we needed was this. We needed that the degree is 6 and the leading coefficient is 1, right? Because it's 1x to the 6th power. Okay, now the leading coefficient, since 1 is positive, since your leading coefficient is positive, that tells me that the right behavior goes up. Okay, positive leading coefficient Polynomials will always do this. If the leading coefficient is positive, out towards infinity, it's going to go up. Now, what about the 6? Since 6 is, doesn't matter if it's, all the polynomials are going to have positive degree. That's not what's coming into play here. But since 6 is even, the left behavior is going to be the same as the right behavior. Okay, and so if you want me to summarize that, what we're saying, where we're getting these ideas, here it is. If all right, let's let f of x be a x to the n plus some stuff. Okay. Now here's how it works. If n is either even or odd, okay, and a is either positive or negative, that alone will determine the behavior. Okay, so here if I have a leading coefficient, I need the right and the left in here, right? Let me zoom in a little bit. So if I have a leading coefficient that's positive, the right side is going to go up regardless of the degree, okay? And if the leading coefficient is negative, the right side is going to go down regardless of the degree. All right, so the leading coefficient determines that strictly. Okay, now for the left side, if if n is even, the right behavior is going to be the same as the left behavior, or the left behavior is going to be the same as the right behavior. So this is going to end up. And here, if a is negative, the leading coefficient would be, the left behavior is down. For the other side, if it's odd, they're going to end up opposite. So if one side's up, the other side's down. Okay, so that's how we're determining our behavior. So what this tells me now, again, in our situation, since we had x to the 6th, my right behavior is up, and since it's even, the left behavior is also up. So now when I come back to my graph, which I'll do again, I know, okay, let's see, my zeros were at -1 and -2 and +3. I know that the right behavior is up. So after 3, this polynomial is going up like this. And I also know the left behavior is up. So after going into the negative direction, -2, it's also going to go up. Now I just got to figure out how this laces up in the middle. And that's where the multiplicities come in play, okay? So I should have at the beginning, when we looked at multiplicities, at -2, is it going to pass through or is it going to bounce? It's going to pass through because it's an odd multiplicity. Okay, so this passes through. At 3, it's going to pass through as well. But at -1, it's going to bounce, or kiss if you want. All right, so let's figure that out. So it's going to pass through at -2. It's going to bounce at -1. Excuse me, pollen. And then it's going to pass through again at 3, something like this. So the middle, we're not going to get exactly correct on the scaling in the middle, but this is the basic shape. Okay, now if you need more information, you could by simply plugging in points. For example, if I look at p of 0 is going to be, let's see, that's going to be 0 plus 2 times 0 plus 1 squared times 0 minus 3 cubed. So that is going to be, well, let's see, 2 times 1 squared times -3 cubed, which is -27. So I get a -54. So this is way down here. This is -54 right here, right? So it's going way down. But this gives me a basic picture of what my polynomial p of x looks like. Does that make sense? I hope it does. So again, it comes down to, is it factored? Okay. Can we determine the end behavior? Yes. Once we just by the degree and the leading coefficient. And then can we find the x-intercepts and multiplicities? Well, if it's factored, yeah, that's very easy to do. And from there, we just connect our information. And notice also, it's a 6-degree polynomial. So how many zeros could we have? We could have at most 6. We only had 3. That's fine. We satisfied that we have at most 6 unique zeros. And then what about the turning points? How many turning points did we have here? We had 1, 2, 3 turning points. We knew that we were going to have at most 5, so we haven't violated any of our rules here. I hope that makes sense. Okay. Let me show you now just a couple of other pieces of information, and then we can actually create a fourth degree polynomial that passes through or has a certain number of zeros that we want. All right, so this is called the conjugate root theorem, and this is related to the complex zeros, okay? So here's what happens. In a polynomial, if you have a complex zero, you're actually going to get two complex zeros because they always show up in pairs. So we say if a plus bi is a zero of polynomial p of x, then so is a minus bi. Okay, in other words, complex roots always show up in pairs. Not just pairs, conjugate pairs. Okay, so if let's think back at the beginning, we looked, the example we had with complex numbers, we had x squared plus 1. And remember how that factored? That factors as x plus I times x minus I. Its zeros are negative I and I. They're complex conjugates, right? And so it's always going to work that way. So that tells me for a third degree polynomial, let's think about it. What are the possibilities? You could either have 3 real roots, or if you have one complex root, you're going to have 2 complex roots. So that means you're either going to have 3 real roots or 1 real root, right? A third degree polynomial always has to have at least 1 real root. And so let me show that again. So let's say p of x is x cubed plus something something. Okay. Well, think about the end behavior. The leading coefficient's positive, the degree is odd, so the end behaviors are going to end in different directions. At some point, it's got to cross the x-axis. So it's either going to do this. It's either going to cross 3 times, or it's only going to cross 1 time. Okay, so it's either going to cross 3 times or 1 time for a cubic polynomial because of the conjugate root theorem. All right, now let me show you an example. This is example 3 in the book. And we're going to list some criterion that we want out of a polynomial, and let's see if we can figure it out. So we want a fourth degree polynomial. So build a fourth degree polynomial with, let's see, with zeros, 2, negative 5, and 1 plus I. Okay, and the other thing that we want to know, such that when I plug in the value 1 into this polynomial f, and we are calling this f of x, we want to get 12. So we want to build a fourth degree polynomial with these 3 zeros that passes through the point f of 1 equals 12. Okay, now what we know, since this is a fourth degree polynomial, we know that this thing's going to look like this. A x to the fourth power plus some stuff. We know that. Alright, but how can we build exactly what this fourth degree polynomial is? Well, let's use the Fundamental Theorem of Algebra. Remember, or the linear factors theorem says that we could break it down based on its zeros as just a product, like prime numbers, as a product of linear polynomials. And since I already know some of its zeros, here's what we know. We know that this thing can be factored as some sort of leading coefficient. We don't know that. But x minus 2, x plus 5, and x minus 1 plus I. We know that, right? Because that's just based off of our zeros. These are my 3 zeros that they gave us. Alright, but look, if you multiplied all this out, you're going to end up with only a third degree polynomial. What about that fourth zero Well, don't forget, conjugate root theorem says if you have one complex number, you get another one as a 0. So my fourth factor here is 1 minus I, like that. So there's my fourth 0. Okay, so now I have a fourth order polynomial. The only thing is I don't know if it passes through that point. Okay, so to make f of x pass through the point 112, here's what we can do. Let's say f of 1 equals a, 1 minus 2, 1 plus 5, 1 minus 1 plus I, 1 minus 1 minus I. And when I know, see, I plugged in the value 1 in for x, and I know when I do that, this thing needs to equal 12. Can I solve for a? Can I get the right leading coefficient that will make this a true statement? Okay, so I think we can do this. We are going to, let's see, that's a times, well, let's see, 1 minus 2 is negative 1, 1 plus 5 is 6, and then here we get some kind of funny stuff. Let's see, 1 minus 1 cancels out, but don't forget to distribute that negative, you get negative I. And then the same over here, you get 1 minus 1, but don't forget you're also having the plus I there, so you have like that. And this has got to equal 12. Okay, I think we're almost there then, because let's see. Negative I times I is negative I squared. That's negative times negative 1, right? Negative I squared is negative 1. So this is positive 1. So I get a times negative 6 times positive 1. So I get negative 6 equals 12. And then now I can divide both sides by negative 6 and end up with a to be negative 2. So now I know exactly what my polynomial is going to look like. The polynomial that we wanted is going to be negative 2 times x minus 2, x plus 5. And if you want this only in real numbers, well, maybe not. Let's just leave it like this for the moment. But I could multiply these two together, and hopefully when I multiply two conjugates together, I'll get just a real number expression. But you know what? For the time being, I think we're good here. So there's our polynomial. Okay, I hope this makes sense, guys. We kind of reviewed some of our material from before, but the Fundamental Theorem of Algebra, what it's helping us do is have a broader perspective of the nature of polynomials. And what we realize now is that the zeros are very, very important. The x-intercepts of a polynomial are very, very important, because what these zeros are doing is it's breaking down a polynomial into its simplest components, just like the prime numbers do with integers. Alright, if you have any questions on this, please let me know. Guys, I hope you're doing well. Get in contact with me if you need some help. I want to make sure you're doing okay. I hope you have a great week. The rest of the week, we'll see you on Monday. And take care. Thanks for watching, guys.